welcome to this problem walkthrough. Today, we'll be exploring an interesting algorithmic challenge, subarray sums divisible by k. In this problem, we'll work through a solution to efficiently determine the number of subarrays whose sums are divisible by a given value, k. Let's dive in and start breaking it down step by step. In this problem, we're tasked with finding the number of subarrays within an integer array, nums, that have a sum divisible by a given integer, k. A subarray is simply a contiguous sequence of elements from the array. For the input, we're given the array nums with a length ranging from 1 to 30,000, where each element can take a value between -10,000 and 10,000. Additionally, we have the integer k, which is a positive number between 2 and 10,000. The output will be a single integer representing the count of these subarrays whose sums are divisible by k. This means the sum of the subarray, when divided by k, leaves a remainder of 0. Now let's look at some examples to understand this better. For the first example, we have the array nums equals 4, 5, 0, -2, -3, 1, and k equals 5. The output is 7, meaning there are 7 subarrays whose sums are divisible by 5. These subarrays are listed, starting with the entire array 4, 5, 0, -2, -3, 1, which has a sum of 5. Then we have 5, which also sums to 5. Similarly, 5, 0, and 0 are valid subarrays with sums of 5 and 0, respectively. Moving on, the subarray -2, -3, 1 has a sum of -5, which is also divisible by 5. Finally, 4, 5, 0, -2, and -3, 1 have sums of 5 and -5, respectively. Each of these sums is divisible by 5, and this gives us the total of 7 subarrays. In the second example, we have nums equals 1, 2, 3, and k equals 3. The output here is 2, since there are 2 subarrays with sums divisible by 3. The first is 1, 2, which sums to 3, and the second is 3, which also sums to 3. For the third example, where nums equals -1, 2, 9, and k equals 2, the output is again 2. Here, the subarrays are 2, which sums to 2, and -1, 2, 9, which sums to 10. Both 2 and 10 are divisible by 2, so we count these 2 subarrays. These examples highlight how sums can be calculated for subarrays, even when the array includes negative numbers. There are a few constraints and edge cases to consider. First, the length of nums is between 1 and 30,000, and each element falls between -10,000 and 10,000. The value of k ranges from 2 to 10,000. For edge cases, if nums contains only one element, the output is 1 if that element is divisible by k, and 0 otherwise. Similarly, if k is greater than the largest possible subarray sum, the output is always 0, since no subarray sum can meet the condition. Finally, if all elements in nums are negative, the solution must still correctly handle the modulo operation to determine divisibility. These constraints and edge cases ensure that the solution is robust and works for all valid inputs. To start, let's consider the brute force approach. The intuition here is straightforward. We want to check every possible subarray in the given array, calculate its sum, and determine if that sum is divisible by k. To achieve this, we use 2 nested loops. The outer loop selects the starting index of a subarray, while the inner loop iterates through all possible ending indices for that subarray. For each combination, we calculate the sum of the subarray and check if it is divisible by k. While this method is simple to implement, its efficiency is a concern. The time complexity is n squared, because of the 2 nested loops, and this makes it impractical for large arrays. However, it has minimal space requirements, with a space complexity of 1, as no additional data structures are needed. The trade-off, then, is between simplicity and performance. This approach is easy to understand but becomes inefficient as the size of the array grows. Now, let's explore the optimized approach using prefix sums and a hash map. This method is based on the insight that if the sum of elements between 2 indices is divisible by k, then the remainders of the prefix sums at these 2 indices must be the same. Here's how it works. As we iterate through the array, we maintain a running cumulative sum. At each step, we calculate the remainder of this cumulative sum modulo k. This remainder helps us track subarrays whose sums are divisible by k. To efficiently count these subarrays, we use a hash map, where the keys represent remainders, and the values store their frequencies. We initialize this hash map with a remainder of 0 set to 1, to account for cases where a prefix sum itself is divisible by k. For each new remainder we compute, we check if it already exists in the hash map. If it does, we add its frequency to our result, since this tells us how many subarrays ending at the current index are valid. Finally, we update the hash map by incrementing the frequency of the current remainder. This approach achieves a time complexity of O(n), as we only iterate through the array once, and the operations on the hash map are constant time. The space complexity is O(k), as the hash map stores at most k remainders. While this method requires extra space, it is minimal compared to the dramatic improvement in efficiency. The chosen strategy for this problem is the optimized approach using prefix sums and a hash map. This method is ideal because it leverages the mathematical properties of remainders to count subarrays efficiently, without the need to explicitly compute the sum of each subarray. The crucial insight is that subarray sums divisible by k can be identified by finding matching remainders in the prefix sums. This eliminates the need for redundant calculations, allowing us to achieve linear time complexity. This approach is not only efficient but also relatively easy to implement once the concept of remainders is understood. The trade-off here is the additional space used for the hash map, but this is a small cost for the significant reduction in runtime. Overall, this strategy strikes the right balance between efficiency, clarity, and practicality. When comparing this approach to alternatives, it becomes clear why the prefix sums and hash map technique is the best choice. The brute force approach, while conceptually simple, is prohibitively slow for large arrays due to its quadratic time complexity. Even less efficient alternatives, like explicitly generating all subarrays, have cubic time complexity and are not practical. In contrast, the optimized approach achieves a significant improvement in runtime, reducing the complexity to O(n), while the space overhead of O(k) is minimal and manageable. This method combines efficiency with elegance, making clever use of mathematical properties to solve the problem effectively. In conclusion, the prefix sums and hash map strategy is the most practical and scalable solution for determining subarray sums divisible by k. The problem requires us to find the total number of contiguous subarrays in a given array of integers where the sum of the elements is divisible by an integer k. To break this down, a subarray is any continuous segment of the array, and for its sum to be divisible by k, the remainder when the sum is divided by k must be 0. One straightforward way to solve this is through a brute force approach. We initialize a counter to keep track of valid subarrays, then use two nested loops to consider all possible subarrays. The outer loop fixes the starting index, while the inner loop iterates through all potential ending indices. For each subarray, we calculate the sum and check if it's divisible by k. If it is, we increment our counter. Finally, after examining all subarrays, we return the counter. However, while this approach works, it has a high computational cost due to its nested loops, making it inefficient for large inputs. To improve upon the brute force method, we can use an optimized approach that leverages prefix sums and hashing. The key observation here is that the sum of a subarray can be expressed as the difference between two prefix sums. If the difference between these sums is divisible by k, then the subarray is valid. This boils down to checking if two prefix sums have the same remainder when divided by k. Using this insight, we can track remainders efficiently with a hash map. We initialize the hash map to store the frequency of remainders, starting with a value of 1 for a remainder of 0 to account for cases where the prefix sum itself is divisible by k. As we iterate through the array, we update the running prefix sum, compute its remainder modulo k, and adjust negative remainders to ensure they are positive. If the current remainder is already in the hash map, it means there are subarrays ending at the current index that are divisible by k, and we add the frequency of that remainder to our counter. Finally, we update the hash map with the new remainder. This approach ensures we only traverse the array once, drastically improving efficiency. The optimized solution relies on a few key insights. First, modular arithmetic allows us to reduce the problem to tracking remainders instead of recalculating subarray sums repeatedly. This simplifies the divisibility check and eliminates redundant calculations. Second, hash maps play a crucial role in making the solution efficient, as they enable constant time lookups and updates for remainders. This reduces the overall time complexity from quadratic to linear. Third, handling negative remainders is essential to ensure the solution works universally, as negative numbers in the array can produce remainders less than 0. By adding k to these remainders and taking modulo k again, we normalize them to a positive range. Lastly, considering edge cases is important. For instance, if all elements are divisible by k, the array will have a high frequency of remainder 0. Similarly, when the array contains negative numbers or when k is much larger or smaller than the array values, the algorithm should still operate correctly. By combining these insights, we ensure the solution is robust and efficient. To implement this approach, we use specific data structures and analyze the algorithm's complexity. The hash map is central to the solution, as it stores the frequency of prefix sum remainders. This allows us to determine, in constant time, how many subarrays end at a given index and are divisible by k. The prefix sum variable tracks the cumulative sum of the array elements as we iterate, eliminating the need to recompute subarray sums repeatedly. Together, these components enable the optimized algorithm to achieve a time complexity of O(n), as we traverse the array only once and perform constant time operations for each element. The space complexity is O(k), since the hash map stores at most k unique remainders. This makes the algorithm highly scalable for large input arrays. The pseudocode for the implementation provides a detailed breakdown of these steps, starting with initializing the counter, prefix sum, and hash map, and iterating through the array to update these values dynamically. The pseudocode continues with the key operations performed during the iteration. For each element in the array, we update the prefix sum by adding the current value, calculate the remainder modulo k, and adjust it to be positive if necessary. Next, we check if this remainder already exists in the hash map. If it does, we increment the counter by the frequency of this remainder, since that many subarrays ending at the current index are divisible by k. Then, we update the hash map by incrementing the frequency of the current remainder. After processing all elements, the counter will contain the total number of valid subarrays. To better understand this process, we can look at an example with the array 4, 5, 0, -2, -3, 1, and k equals 5. Initially, the prefix sum and counter are 0, and the hash map is set up with a remainder of 0 having a frequency of 1. As we iterate through the array, we update these values dynamically, identifying subarrays divisible by k and incrementing the counter accordingly. In the example, we start with the first element, 4, which gives a prefix sum of 4 and a remainder of 4. This remainder is added to the hash map. Moving to the next element, 5, the prefix sum becomes 9, with the same remainder of 4. Since remainder 4 already exists in the hash map, we increment the counter by its frequency, indicating one valid subarray ending at this index. The hash map is then updated with the new frequency of remainder 4. As we continue processing the array, similar calculations are made for each element. At index 2, the prefix sum remains 9, and the counter increases again due to the repeated remainder. This process continues until the end of the array. By the final element, the counter is 7, indicating that there are 7 subarrays whose sums are divisible by k. This example demonstrates how the algorithm efficiently tracks remainders and counts valid subarrays, achieving the desired result with minimal computation. This solution efficiently solves the problem using a prefix sum and a hash map to track remainders. Here's how it works. 1. Initialization. We start by initializing 3 variables. Prefix _sum to keep track of the cumulative sum of the array as we iterate through it. Count to store the total number of valid subarrays we find. Remainder _count, a dictionary initialized with 0, 1, to track how many times each remainder is encountered. This helps identify subarrays whose sums are divisible by k. 2. Iterating through the array. For each number in the input array, we add it to the prefix _sum. 3. Calculating the remainder. After updating the prefix _sum, we calculate the remainder of prefix _sum %k. Since Python can return negative remainders, we adjust it to be non-negative by adding k if the remainder is less than 0. For checking remainders, if the current remainder has been seen before in remainder _count, it means there exists at least one subarray ending at the current index whose sum is divisible by k. we add the count of this remainder from the dictionary to our count variable. 5. Updating the hash map. We update the frequency of the current remainder in the remainder_count dictionary. If the remainder is not already in the dictionary, we add it with a frequency of 1. Otherwise, we increment its frequency. 6. Returning the result. After iterating through all the numbers, count contains the total number of subarrays whose sums are divisible by k, and we return it. This algorithm runs in O(n) time because we process each element of the array exactly once and perform constant time operations for each element. The space complexity is O(k) due to the hash map storing remainders, making it efficient for large inputs. Here, we start by importing the necessary libraries and defining our solution class. The method subarrays div by k takes an integer array nums and an integer k as inputs. First, we initialize three key variables: prefix sum to keep a running sum of the elements, count to track the number of subarrays that meet the condition, and remainder count, a hash map that will store the frequency of remainders when prefix sum is divided by k. To handle the base case, we pre-populate the map with a remainder of 0 and a count of 1, since a prefix sum divisible by k can start from the beginning of the array. Now, in the loop, we iterate through each number in the nums array, adding it to prefix sum. We then compute the remainder of prefix sum modulo k. Since remainders can sometimes be negative depending on the sign of the prefix sum, we adjust it by adding k to ensure it's always non-negative. This ensures consistency when we check the map later. Next, we check if this remainder has been seen before in the map. If it has, it means there are subarrays ending at the current index that are divisible by k, so we add the frequency of this remainder to the count. After that, we update the map by incrementing the frequency of the current remainder, or initializing it to 1 if it's the first time we've seen it. Finally, after processing all the elements in the array, we return the count variable, which holds the total number of subarrays whose sums are divisible by k. This approach is efficient, with a time complexity of O(n), since we traverse the array once, and all operations involving the hash map are constant time on average. By leveraging the prefix sum and remainder tracking, we avoid the need for nested loops, which would have increased the complexity. This completes the implementation. Here, we start with the first example where nums is 4, 5, 0, -2, -3, 1, and k is 5. Our initial setup includes the prefix _sum set to 0, count initialized to 0, and remainder _count starting with 0, 1, to account for subarrays that are directly divisible by k. In the first iteration, the current number is 4, so we add it to prefix _sum, making it 4. The remainder when 4 is divided by 5 is also 4. Since there's no previous occurrence of this remainder in remainder _count, we simply update the dictionary to include it, resulting in 0, 1, 4, 1. No subarray ends here with a sum divisible by k, so count remains 0. Next, with the second number, 5, prefix _sum becomes 9, and the remainder when 9 is divided by 5 is again 4. This time, remainder _count already has 4 with a value of 1, meaning there's one subarray ending here with a sum divisible by 5. Thus, we increment count by 1, making it 1, and then update remainder _count to 0, 1, 4, 2. In the third iteration, the current number is 0. Adding this to the prefix _sum keeps it at 9. The remainder remains 4, and now remainder _count shows that the remainder 4 has occurred twice before. This indicates there are two subarrays ending at this point with a sum divisible by 5. Therefore, we add 2 to count, bringing it to 3, and update remainder _count to 0, 1, 4, 3. Moving to the fourth number, -2, prefix _sum becomes 7. The remainder when 7 is divided by 5 is 2. Since this is a new remainder, we add it to remainder _count, resulting in 0, 1, 4, 3, 2, 1. For the fifth number, -3, prefix _sum updates to 4. The remainder is once again 4, and remainder _count shows that this remainder has occurred 3 times previously. This tells us there are 3 subarrays ending here with a sum divisible by 5. We add 3 to count, which now becomes 6, and update remainder _count to 0, 1, 4, 4, 2, 1. In the final iteration of this example, the current number is 1. Adding this to prefix _sum gives us 5. The remainder when 5 is divided by 5 is 0, and remainder underscore count shows that this remainder has occurred once before. This means there is one subarray ending here with a sum divisible by 5. Adding 1 to count brings the total count to 7. We then update remainder underscore count to 0, 2, 4, 4, 2, 1. With all iterations complete, the final output for this example is count equals 7. Now we look at the second example where nums is 1, 2, 3, 4, 5, and k is 3. Again, we initialize prefix underscore sum to 0, count to 0, and remainder underscore count to 0, 1. For the first number, 1, adding it to prefix underscore sum gives a value of 1. The remainder when 1 is divided by 3 is also 1. Since this is a new remainder, we add it to remainder underscore count, resulting in 0, 1, 1, 1. For the second number, 2, prefix underscore sum becomes 3. The remainder when 3 is divided by 3 is 0, and remainder underscore count shows that this remainder has occurred once before. This indicates one subarray ending here with a sum divisible by 3. Adding 1 to count makes it 1, and we update remainder underscore count to 0, 2, 1, 1. Next, for the third number, 3, prefix underscore sum updates to 6. The remainder when 6 is divided by 3 is 0. Remainder underscore count indicates that this remainder has occurred twice before, meaning there are two subarrays ending here with a sum divisible by 3. Adding 2 to count brings it to 3, and remainder underscore count is updated to 0, 3, 1, 1. For the fourth number, 4, prefix underscore sum becomes 10. The remainder when 10 is divided by 3 is 1, and remainder underscore count shows that this remainder has occurred once before. This indicates one subarray ending here with a sum divisible by 3. Adding 1 to count makes it 4, and we update remainder underscore count to 0, 3, 1, 2. Finally, for the fifth number, 5, adding it to prefix underscore sum results in 15. The remainder when 15 is divided by 3 is 0. Remainder underscore count shows that this remainder has occurred 3 times previously. This means there are 3 subarrays ending here with a sum divisible by 3. Adding 3 to count brings the total count to 7, and we update remainder underscore count to 0, 4, 1, 2. With all iterations complete, the final output for this example is count equals 7. In the third example, nums is -1, 2, 9, and k is 2. As before, we initialize prefix underscore sum to 0, count to 0, and remainder underscore count to 0, 1. For the first number, -1, prefix underscore sum becomes -1. The remainder when -1 is divided by 2 is initially -1, but we adjust it to its non-negative equivalent, which is 1. Since this is a new remainder, we add it to remainder underscore count, resulting in 0, 1, 1, 1. For the second number, 2, prefix underscore sum updates to 1. The remainder when 1 is divided by 2 is 1, and remainder underscore count shows that this remainder has occurred once before. This means there is one subarray ending here with a sum divisible by 2. Adding 1 to count makes it 1, and we update remainder underscore count to 0, 1, 1, 2. Finally, for the third number, 9, prefix underscore sum becomes 10. The remainder when 10 is divided by 2 is 0, and remainder underscore count shows that this remainder has occurred once before. This indicates one subarray ending here with a sum divisible by 2. Adding 1 to count brings the total count to 2, and we update remainder underscore count to 0, 2, 1, 2. With all iterations complete, the final output for this example is count equals 2. The time complexity of this solution is O, n, where n is the length of the input array nums. This is because the algorithm processes each element of the array exactly once. During this single iteration, several constant time operations are performed for each element. These include adding the element to the prefix sum, computing the remainder using the modulo operation, adjusting the remainder to ensure it's non-negative, and updating or accessing the remainder underscore count dictionary. Since these operations are all O1, the total work for each element is O1. With n elements in the array, the overall time complexity becomes O(n). This guarantees that the solution is efficient even for large input arrays. Now, let's examine the best, average, and worst-case scenarios for the time complexity. In all cases, whether the array has repeated elements, all unique values, or any other configuration, the algorithm completes in O(n), because it always processes the input array in a single pass. The operations inside the loop consistently remain O(1) on average, even if the dictionary grows to store more remainders. Thus, the time complexity is O(n) in the best, average, and worst cases. For space complexity, the key factor is the remainder_count dictionary, which stores the frequencies of remainders encountered during the iteration. The number of unique remainders is limited to the range 0, k1, meaning at most k unique keys will exist in the dictionary. If the size of the input array n is smaller than k, the dictionary will only store up to n keys. Therefore, the space complexity for this dictionary is O(min n k). Additionally, the space usage includes scalar variables such as prefix_sum, count, and remainder, which require constant space, or O(1). Combining this with the dictionary's space usage, the overall space complexity of the algorithm is O(min n k). To provide some context, let's compare this optimized approach to a naive solution. The brute force approach would involve generating all possible subarrays of nums and calculating their sums to check divisibility by k. This would result in a time complexity of O(n³), as generating all subarrays takes O(n²), and calculating each subarray sum adds another O(n). In contrast, our optimized approach reduces this to O(n), a significant improvement. Furthermore, while the brute force approach requires only O(1) additional space, the optimized solution uses O(min n k) for the hash map, which is still highly efficient for large inputs. The optimized solution achieves its efficiency by leveraging the prefix sum technique and a hash map to store remainders and their frequencies, replacing the need to generate all subarrays. This reduces the time complexity from O(n³) in the brute force approach to O(n). Although the space complexity increases from O(1) in the naive solution to O(min n k) due to the hash map, this trade-off is well worth it for the significant improvement in runtime. Mathematically, the time complexity is derived from the fact that each of the n elements contributes O(1) work, leading to a total complexity of O(n). Similarly, the space complexity is determined by the maximum possible size of the remainder dictionary, which is limited to min n k. This balance of efficient time and manageable space usage makes the optimized solution a robust choice for solving the problem, even with large input sizes. One common mistake when tackling this problem is ignoring how different programming languages handle negative remainders during modulo operations. For instance, in Python, performing -4%3 gives you -1, which might not align with the problem's requirements. To ensure correctness, you should adjust such negative remainders by adding k to bring them into the range 0, k1. This adjustment is crucial for maintaining consistent logic. Another frequent pitfall is neglecting edge cases. You need to consider scenarios like subarrays of length 1 or when k is 0. If the problem permits k being 0, you must handle it explicitly, as it can lead to runtime errors. For example, a situation like nums equals 0, with k equals 0 may require special handling. Finally, attempting to solve this using a brute force approach with nested loops can result in unacceptable performance. The time complexity of such an approach is O(n³) in the worst case, which is impractical for constraints where n can go up to 10,000. Optimizing your solution is essential to avoid timeouts. Another issue to be mindful of is misunderstanding modulo properties. For example, while a plus b %k == 0 may hold true, it doesn't necessarily mean that a %k == 0 and b %k == 0. Misinterpreting this property can lead to logical errors. Instead, rely on the prefix sum approach combined with modular arithmetic to simplify your checks for subarray divisibility. Additionally, off-by-one errors are a common source of bugs. When iterating over subarrays or defining ranges, it's easy to accidentally include or exclude indices incorrectly. For instance, iterating from I to j instead of I to j plus 1 could lead to missing valid subarrays. From an interview perspective, it's important to focus on optimization strategies. Interviewers often expect you to identify inefficiencies in brute force solutions and transition toward optimized techniques like prefix sums or hash maps. Be sure to clearly articulate your reasoning, especially when adjusting negative remainders or tracking remainders in a hash map. Discuss edge cases thoroughly, including when k is 0 or all elements are negative. Lastly, consider space complexity trade-offs, as hash maps, while efficient, do increase memory usage. Being able to weigh these trade-offs demonstrates a deeper understanding of the problem. If you want to deepen your understanding of this topic, several related problems are worth exploring. For instance, in the problem Subarray sum equals k, LeetCode 560, a similar prefix sum approach is used, but the focus shifts to finding exact subarray sums rather than checking divisibility. Another closely related problem is continuous subarray sum, LeetCode 523, which also involves subarray sums and divisibility by k. For variations, you might encounter problems like longest subarray with sum divisible by k, which focuses on finding the longest valid subarray instead of simply counting them. Similarly, maximum size subarray sum equals k, LeetCode 325, requires identifying the longest subarray with a specific sum. These problems all build on the concepts of prefix sums and modular arithmetic, so mastering one can make it easier to tackle others. To solve this problem efficiently, the most common approach is to use a prefix sum combined with a hash map. The hash map keeps track of the remainders seen so far, reducing the time complexity to O(n), while maintaining a space complexity of O(n). However, this optimization comes with a trade-off: the increased memory usage from storing the hash map. For some related problems, a sliding window approach might be applicable, but it's less suited for this problem, as divisibility checks don't naturally lend themselves to sliding window techniques. Sliding windows also require careful management of subarray boundaries, which can increase the risk of errors. Alternatively, dynamic programming can be employed for variations of the problem that include additional constraints, such as finding the longest subarray. While DP can simplify handling complex constraints, it often comes at the cost of higher time complexity, potentially reaching O(n squared), depending on the state space. Choosing the right approach depends on the specific requirements and constraints of the problem you're solving. Great job! In this problem, we explored an efficient way to solve the subarray sums divisible by k challenge. By using prefix sums and modular arithmetic with a hash map, we achieved an optimal solution with O(n) time complexity. Remember, these strategies are useful for similar subarray and modular problems. Thanks for tuning in. Please like and subscribe for more content, and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!